Hello, my name is Devin Allison, and I will be talking about elliptic curve arithmetic. This is section 10.3 in the book, if you'd like to go and take a look. So first we're going to define what an elliptic curve is. So an elliptic curve is an equation of two variables, x and y, and it has the following form. This is called Weierstrass form, where y squared plus axy plus by equals x cubed plus cx squared plus dx plus e. For cryptography, we can simplify this down to y squared equals x cubed plus ax plus b. We have an additional constraint on this where 4a cubed plus 27b squared does not equal 0. If this equality was true, then we would have duplicate roots, and one point would give you multiple zeros. So one thing you can tell from the simplified form is that these are going to be symmetric about the x-axis, which is something we're going to use when we're talking about elliptic curve addition. So here's an example of what an elliptic curve looks like. In this case, a is 1 and b is 1, so we can write this curve as e of 1 comma 1. Also, y squared equals x cubed plus x plus 1. I just did this in Wolfram, and this is what it looks like. You can see it's symmetric about the x-axis. We're going to define addition on an elliptic curve in such a way that it forms an abelian group. So as a refresher on what those constraints are, to be in a abelian group, you have a group G and an operation dot, and that operation is closed over G. So if you have 2 points in G and you apply the operation to them, then the result is also in G. It's associative, so a dot b dot c equals parentheses a dot b parentheses dot c. There's an identity element, so there's an element in the group such that when you apply the operation to it, you just get the original element back. There's an inverse, so for every element in the group, there's another element in the group that when you apply the operation to both of those, you get the identity back. And then the operation is also commutative, so a dot b equals b dot a for all a comma b in G. So keep these rules in mind as we're going through addition. The only one that's hard to see is associativity. We're not going to prove it because the proof is actually pretty tough, but all of these will be true. So suppose we want to add 2 points on our curve, so P and Q on this graph. There's a geometric way to define addition, and this is what it is. You draw a line between P and Q, and you extend that until it hits our curve, E. So you can see that top dashed line going through P and Q. You find where that intersects E, and you draw a vertical line through that point, through that intersection, and you find where that intersects E as well. So there's a whole bunch of cases there, and we're going to go through them. So our set's going to consist of all the points on the curve, as well as this element 0, or also called the point at infinity. I like the 0 notation because this is our additive identity, and 0 is our additive identity in the real numbers. So this is something we include for the abelian group. Remember, we need an identity, so any point P plus our 0 point is going to be P. An abelian group also needs an inverse. So in elliptic arithmetic here, we define the additive inverse in the following way. So you take the point P on our curve, we draw a vertical line through it, and find where that intersects our curve E. So that's that picture on the bottom right. And the point where that intersects is going to be our additive inverse. And because this is symmetric about the x-axis, then the additive inverse of P, where P is x comma y, is going to be x comma negative y. So in a abelian group, we also need to define what the inverse is. So in an elliptic curve, we would define the inverse in the following way. So if you have the point P on our curve, you would draw P, or draw a vertical line through P, and find where that line intersects E. So that's what's happening in the bottom right, on that graph on the bottom right. And that point of intersection is the additive inverse. So because this is symmetric about the x-axis, the additive inverse of a point x comma y is actually going to be x comma negative y. And you can see that we say that that's just defined as negative p. So there's another case where when you draw that vertical line, there's no second point where that line intersects the curve. So in our graph at the bottom there, that would be on that far left, where the vertical line would lie tangent to our curve. And in this case, we actually say the point itself is the additive inverse. So in that case, p plus p would be that point at infinity. So where neither p or q are 0, we define addition in the following way. We talked about this before, where we have p plus q, we draw the straight line between them, and we find where this line intersects E. So there's going to be 3 different possibilities here. So one of them is you drew the line through P and Q, and the line is tangent to the curve E at P, in which case there's not going to be another intersection with our curve E. So in this case, we would say that P plus Q is equal to negative P. So the way you can think about it is, if it's tangent to that point, then it's like it's hitting it twice. So it's intersecting it twice. So in which case, we would give the negative of that intersection. So it's the same thing if the line is tangent at Q, then we would say that it's hitting the curve at Q twice, in which case P plus Q is equal to negative Q. And then that third point is the one that we discussed. So this is the kind of the simplest case where it intersects at a unique third point, in which case it's P plus Q is defined as the negative of that point. So that's that graph again, where we drew the line through P and Q. We found that unique point intersection. If we call that R, then P plus Q will be equal to negative R, or the additive inverse of R. So you can solve for P plus Q algebraically. So this is the case where the straight line between P and Q intersects at that unique point R. So in that case, the slope of the line is this delta, and that's just simple rise over run. So y sub q minus y sub p over x sub q minus x sub p. And those are the equations that you would solve for x sub r and y sub r. And we're going to run through an example later. And we have one last case where we're adding a point to itself, and it's pretty analogous to the regular addition. So we're drawing a point, or we're drawing a line through P that is tangent to our curve. So that's what's going on in that bottom left. There's 2 cases. The one is that there's no intersection of that line with our curve E, in which case, as before, we're saying that the P is its own additive inverse. So P plus P is the identity. Otherwise, it's going to be the same as any other addition. So P plus P, you would find that intersection with E, and you'd find the additive inverse. So that's that point R at the bottom. And these are the algebraic equations you would get to solve that problem. So it's a little more messy. We can also define this addition over different number systems. So one we're familiar with is the set of integers mod p. And in this case, it's going to be basically the same math, just with this mod p operator applied to everything. So in this case, all coefficients and points will be between 0 and p minus 1. The equations are going to be the same with the mod p. So y squared mod p equals x cubed plus ax plus b mod p. And you can see that these are the same equations as before, just with that mod p. This is a finite abelian group if 4a cubed plus 27b squared mod p does not equal 0. And we would notate this as e sub p of a and b. And this is an example of an elliptic curve, e sub 23 of 1 comma 1. So in this case, p is 23, a is 1, and b is 1. And you can see that it's still symmetrical about a certain y value, in this case y equals 11.5. And we're going to see that the addition actually follows the same geometric idea of drawing the line, finding the additive inverse of the intersection. So we're going to run through an example. So suppose we want to add p and q, where p is equal to 3 comma 10 and q equals 9 comma 7 in that curve e sub 23 of 1 comma 1. So we first find our slope. That's just rise over run. So it's y sub q minus y sub p over x sub q minus x sub p. So 7 minus 10 over 9 minus 3 mod 23. Well, that's the same as negative 1 over 2 mod 23. And remember, division in z sub p is just multiplication by the multiplicative inverse. So negative 1 over 2 is the same as negative 1 times the multiplicative inverse of 2. And the multiplicative inverse of 2 mod 23 is 12. So this is negative 12 mod 23, which is 11. So we can plug this slope into our above equations to solve for x sub r and y sub r. So x sub r is 11 squared minus 3 minus 9 mod 23, which is 17. And y sub r is 11 times 3 minus 17 minus 10, which is 20 mod 23. So in this case, p plus q is 17 comma 20. And we can show that on our graph, and you can see that I've drawn a line between p and q. So there's the 3 comma 10 and 9 comma 7 points. It intersects our curve at 17 comma 3. So we find the additive inverse of 17 comma 3 in mod 23, and that's 17 comma 20. So that's where the y values sum up to 0 in mod 23. So the same geometric idea of addition from our real numbers also carries over to the integers mod p. We can also do this arithmetic in the Galois field of 2 to the m. So the equation is going to be a little bit different in this case, where it's a little more complicated. We have this form y squared plus xy equals x cubed plus ax squared plus b. So we have this extra xy term. So the math's going to be a little bit different. The equations are going to be a little bit different. But the idea is going to remain the same. And again, every point and coefficient are in GF of 2 to the m. We have an additional constraint to make this a finite abelian group where b cannot equal 0. So addition in GF of 2 to the m is defined in the following way. Again, we have every point on our curve along with the identity element, the point at infinity, and p plus that identity is always p. We define the additive inverse. Remember, we need an additive inverse for an abelian group, and it's defined a little bit differently than before. So if we have a point p equals x comma y, then the additive inverse is going to be x comma x plus y. So p plus the inverse is the identity, or 0. The addition, this is just another algebraic formula that they solved for, where lambda here is again the slope, so that's rise over run. In GF of 2 to the m, addition and subtraction are the same thing, so they're just using addition here. And you can see that the equations are a little more complicated because we had the xy term in our elliptic curve. And the last case is where we're doubling a point, so we're adding a point to itself. And this is the algebra for that. So let's run through an example of this. Let's suppose we have the finite field gf of 2 to the 4 with the irreducible polynomial f of x equals x to the 4th plus x plus 1. So this gives us the generator g equals 0, 0, 1, 0. That's the binary form. And if we go through and solve all the powers of g, that'll give us this chart. So g to the 0 is 1, g to the 1 is itself 0, 0, 1, 0. G squared, you just multiply x by x, you get x squared, so it's 0, 1, 0, 0 in binary, and etc. And that would fill that chart out. In our example, the elliptic curve is y squared plus xy equals x cubed plus g to the 4th x squared plus 1. So in this case, a is g to the 4 and b is 1, and we're in gf of 2 to the 4. They've graphed this with g equals 0, 0, 1, 0, where all of these points are on our curve. And you can see we've lost that symmetry that we had before. So if we want to solve p plus q, where p equals g to the 5th, g to the 3rd, and q is g to the 6th, g to the 8th, then we first solve for our slope, or our lambda. So that will be yq plus yp over xq plus xp. So that's g to the 8th plus g to the 3rd divided by g to the 6th plus g to the 5th. So just using our chart we solved before, g to the 8th is 0, 1, 0, 1, g to the 3rd is 1, 0, 0, 0, g to the 6th is 1, 1, 0, 0, g to the 5th is 0, 1, 1, 0. And remember, addition in gf of 2 to the m is just a XOR. So we do a bitwise XOR to solve these additions, and we get 1, 1, 0, 1 divided by 1, 0, 1, 0. And as in the case with the integers mod p, division is just multiplication by the inverse, by the multiplicative inverse. So I switched these back to be powers of g because multiplication is easier that way. 1, 1, 0, 1 is g to the 13th. 1, 0, 1, 0 is g to the 9th. So the inverse of g to the 9th will be g to the 6th. And we have g to the 13th times g to the 6th is g to the 19th, which is g to the 4th in 2 to the 4. So we can use this value of lambda, g to the 4, and plug that into our equations for x sub r and y sub r. So x sub r equals lambda squared plus lambda plus x sub p plus x sub q plus a, which is g to the 4th squared plus g to the 4th plus g to the 5th plus g to the 6th plus g to the 4th. Those g to the 4ths cancel, and g to the 4th squared is g to the 8th. We use our chart. G to the 8th is 0, 1, 0, 1, g to the 5th is 0, 1, 1, 0, and g to the 6th is 1, 1, 0, 0. Perform the bitwise XOR for addition, and this gives us 1, 1, 1, 1, or g to the 12th, and we can plug that into our equation for y sub r. So y sub r is lambda times x sub p plus x sub r plus x sub r plus y sub p. That gives us g to the 4th times g to the 5th plus g to the 12th plus g to the 12th plus g to the 3rd. G to the 5th plus g to the 12th is 0, 1, 1, 0 plus 1, 1, 1, 1, which is 1, 0, 0, 1, or g to the 14th. Go back to the g to the power notation because we're doing multiplication. G to the 4th times g to the 14th is g to the 18th, which is g to the 3rd in 2 to the 4th. So y sub r will be g to the 3rd plus g to the 12th plus g to the 3rd. Our g to the 3rds cancel, and we just get g to the 12th, or 1, 1, 1, 1. So p plus q here is g to the 12th, comma g to the 12th. And you can see on our graph that we don't quite have the same geometric interpretation. So the inverse, the additive inverse of g to the 12th is that point g to the 12th comma 0 up at the top, because remember the additive inverse is x plus y. So in this case, g to the 12th plus g to the 12th, which is just 0. And maybe there's a way to draw this line so that, maybe it wraps around and intersects g to the 12th comma 0 at some point. But I couldn't get it to do that. So to me, this really doesn't have that geometric definition that the real numbers or the integers mod p had. It's just the same algebra that we would derive this from.